Okay, nerds, so we're back at it. Part two of the lesson for transformations. We have already learned about translations. We talked about those yesterday. And what we said was anytime you add or subtract inside your equation, well, in your equation, I should say, anytime you see any addition or subtraction in your equation, then that is definitely a shift. So we worked all of our shift magic. We said that vertical changes are up down changes, are y changes. We said that those are always going to happen on the outside and they have the same effect that we expect them to have. And we said that our horizontal changes, our x changes, will always happen on the inside and they have the opposite effect as what we expect. And that's what we talked about yesterday. Today, we are going to tackle reflections and then we'll move on to stretching and shrinking. But right here for reflections, I need you to just kind of realize that my whole inside opposite effect thing is not a law. It's like a rule. And you know, some rules can be broken. It doesn't really apply very well to reflections. And the reason why is because all reflections, and we're only going to deal with two, reflect over x, reflect over y, all reflections that we're going to deal with will simply be us multiplying by -1 somewhere. You either have a multiplier of -1 on the inside, or you have a multiplier of -1 on the outside. So the whole inside stuff does the opposite effect of what we expect. It doesn't really work very well because either you reflected or you didn't. Okay, so we won't be able to say opposite effect for this. But I've already mentioned that reflections will always be a -1 multiplier. You see a multiplier of a negative somewhere, that's a reflection, guaranteed. This is one of the hardest transformations for students to learn. And it's not because they don't know how to reflect things. It's because they forget which rule goes with which axis. So I've got this image over here to help us out. So check this out. This is your x-axis. If you reflect over the x-axis, and this is lots of people's voices, this kind of motion, is it horizontal or is it vertical? Vertical, okay. And if it's a vertical change, am I changing my x's or my y's? Y. All right, so there is the issue. When you say reflect over x, it changes your y's. And that students will get those two things confused. They say, oh, reflect over x, change x. No, 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 no. Reflect over x, you can see it's an up-down motion set changes the y's. How does it change the y's? Well, f of x means y values. It literally takes your y values and multiplies them by -1. Which is what I have in this image. This dot, if it was positive x, positive y, and you multiplied your y values by -1, you'd end up down here at -y. So if I do this, if I have to reflect over the x-axis, I have to remind myself that that is an up-down motion. That means I'm changing my y's, which means I'm changing my outside, and that is why this rule will be -1 times f of x. Now I know I didn't put a -1, I just put a negative, but they mean the same thing. Now this one here, and lots of voices. If this is a left-right motion, is that going to be an x change or a y change? X change. So you can see that when I do this, my pen is crossing the y-axis. So when you say reflect over the y-axis, you have to realize it's x that you are changing. And if it is x that you are changing, it's going to happen on the inside. What is it doing? The transformation is literally multiplying your x's by -1. So if you went from here to here, the only thing that was different was x. The symbol changed. So you're going to multiply x by -1. Now this is for your coordinates. Multiply x values by -1. Because I can't just multiply this x by -1. Remember, if something on the inside changes, it is a 100% substitution. Replace your x with -x. And you'll see that happen in the notes when we do it. So here, because I crossed over the y-axis, reflecting over the y-axis, I'm forced to move left and right. If it's a left-right motion, it's x that's changing, which forces me to be doing a replacement of x with -x. It multiplies your x values by -1. And there it is. And even though I've got a degree in math, and even though I've been teaching these thingamabobs forever, I still managed to goof up these rules in first period because I was saying X a bunch of times and I put my symbol on the X. So it's very easy to goof it up. And because of that, whenever I have to do any kind of reflection style questions, I typically will just draw this cheesy little image like this off somewhere on my scrap paper or on my work, just somewhere, just to make sure I'm doing it right. And then I do this. Let's say f of x was only in that top right quadrant. This is x, this is y. And then I ask myself, if this reflected to down here, I ask myself, what way did I move? I moved up, down. That's my y change. And all y changes happen on the outside. That means the rule is -1 times f of x. And I draw this. I ask myself, which way did I move? I see that that was a left-right movement, which means I'm clearly altering my x's, and all x changes happen on the inside. So then this is the rule. And I've never seen this little image in any textbooks anywhere. That's what I created for myself when I was trying to master these things a billion years ago. I don't think it takes much time or effort to put it there, and I do know that putting it there, it ensures that you're much less likely to make the mistake that I made in first period. And luckily someone was like, shouldn't that have been on the inside? And I was like, yes, I did the wrong symbol, or on the outside, whatever it was, but I definitely did it backwards. Which is why I don't record period 1, because that's where I make my mistakes. So here we have a function. You have no idea what it looks like, more than likely. You can't see that. You don't know what it looks like. We'll graph these later in the year, but you don't need to know. We're going to find the new equations that we will get by reflecting over each of the two axes. We can do that without knowing what the graph looks like because transformations affect all graphs the same. Transformations affect all functions the same. That's why we like them so much. I'm going to go ahead and segment off this area so we can do reflections. On this side, let's reflect over x-axis. Reflecting over x, I come up here, I reference the thing that reminds me what my rule is. Oh, there's my rule. That's my rule. Because we're reflecting over x, that's an up-down motion. So the rule is -1 times f of x. And now I'm going to put that rule into play. Let me write my f of x. There. In order to reflect this over the x-axis, I will need to multiply that left side by -1. If you do it to the left side, you need to do it to the right side. Please be in the habit of using parentheses when you multiply a side by anything. Please be in the habit of using these parentheses. Now, -1 is a whole number. If you wanted to write it as a fraction, it would be -1 over +1. Or you could say it's 1 over -1. But my question to you, and it's a yes or a no question, is, do I distribute this negative sign to the top and the bottom at the same time?
No.
No, you do not. You pick one of them. Either the top, if you're saying this is -1 over 1, or the bottom, if you're saying this is 1 over -1. But never to the top and the bottom. Because if you distribute a negative to the top and the bottom, a negative divided by a negative is a positive, and you've actually done nothing. So we're going to get 3 different ways that this answer could be written, and we do need to change this thing's name because we've transformed it. We'll call it G because that is the next letter in the alphabet. 3 different acceptable ways of writing this. You could do the lazy thing and just put the negative symbol in front of that fraction. Or you could distribute it to the numerator, so distribute it across the top to get -5x plus 9 all over x squared plus 3. Or you could be strange and distribute it to the denominator. And the reason why I say that's strange is because you don't want that negative on that x squared if you can avoid it. It's just a little weird. So if this was my test, I would never write an answer like that in my multiple choice answers. It would look like this or this. There's nothing wrong with this. Mathematically, all three of those are exactly the same thing. It just looks weird. Makes me a little uncomfortable. I don't know. So it'll be cool with either one of these. But that is what your g of x would be. Would you like to ask me any questions about finding that g of x? No. Okay. If I knew how to edit videos, I would have inserted a cricket's chirping sound right there in my video. That would have been awesome, but I don't know how to do that. Tell me that would have been cool, right? That would have been good. All right, let's do this. Reflect over the y-axis. So if I'm reflecting over the y, here's y. Reflecting over the y forces me to move in a left-right fashion. If I'm moving left-right, that's changing my x's, which is why the negative is on the inside. So the rule would be this. It's a substitution. I will replace every x with a set of parentheses, and I will fill those parentheses with negative x. Everywhere my original function had an x, I have an open set of parentheses. Filling those parentheses with a negative x on the left forces me to fill those parentheses with the negative x on the right. And now I'll clean it up and I'll write the whole thing in green. We'll give it a new name. I can't call it G because this is G. So FGH. H is the next letter in the alphabet. English is hard. Okay. 5 times negative x is negative 5x. Now in the denominator, negative x quantity squared means negative x times negative x. If you multiply those two negative numbers together, you get a positive result. And x times x is x squared. So there is our h of x. I could factor a negative 1 out of the numerator and make the numerator say 5x plus 9 if I wanted to. You don't need to, but I do want to make sure that you are comfortable with the fact that that is this. If you undistribute the negative sign, these are the same answer. There's no such thing as which one's better, but I know me, and I know on a test for me, the answer probably would look like that. And this answer would probably look like that, just because I feel like it's the best way to see a fraction. But that's a me thing, it's an opinion. As long as you are comfortable factoring a negative 1 off of the top of a fraction or factoring a negative 1 off the bottom of a fraction and moving it to the front, then you're fine. Do you have any questions for me about reflecting over either axis? Insert cricket sounds here. Okay. Well, tell you what. How about a little bit of spiral review? Something that this lesson wasn't meant for you to definitely notice, but it is good math. So we'll talk about it. I've left myself some space here. I should have left myself a little bit more space. I'm going to write some stuff here. This is not the only time this year, and this is only our third week. We're only ending our third week, but this is not the only time in our first 3 weeks together that I have told you replace x with negative x. This is also how we checked for even and odd symmetry. The reason why this is how we check for even and odd symmetry is because even and odd symmetry is looking for very specific types of transformational reflections. They're looking for equivalent reflections. Now, I didn't want to say that before when we were doing even odd symmetry. Instead, I used my little hand trick. It's like, okay, that's not, doesn't work very well on the camera, does it? Oh well. Yes, there's some things you have to be in person to see. But when I put my hands together like that, and I said where my thumbs were touching, that had to be the y-axis for them to be even, right? Okay, check this out. You can see my watch is on my left hand. My thumbs are touching the y-axis. I'm going to reflect this graph, which is my hands, over the y-axis. You ready? Same picture. But now the watch is on what looks like, what did I say last time? Did I say left? Okay, that's my left, but it's your right. I'm so sorry. Your right side had a watch on it. When it reflects over the y-axis, now your left side has a watch on it. But it was the exact same image. So reflecting over the y-axis produced the same image. Okay? Now what about odd symmetry? This one really won't work on camera. There's no way I'm getting my hands in there like that, right? Okay. Odd symmetry says reflecting over the x-axis is the same as reflecting over the y-axis. So if I do it like this, you see my hands are in the top left and bottom right, correct? Just making sure that I said the correct direction. So top left, bottom right. I'm going to reflect this over the x-axis. Now they're in the top right, bottom left, correct? Great. Now I went back to top left, bottom right, and I'm going to reflect over the y-axis. Top right, bottom left. So when you're talking about even and odd symmetries, you're actually talking about reflections that match each other. So spiral review. Both tests required me to plug in negative x. When I plugged in negative x, this was my result. Either one of these, they are the same thing. Is either one of these identical to the original function? You guys can shout it out.
No.
No, it is not. Because reflecting over the y-axis, had to be really careful. I actually looked at my own little image to make sure I said the right axis. Because reflecting over the y-axis did not give me the exact same equation, this is not an even function. But both types of symmetries require reflecting over the y-axis. Did reflecting over the y-axis end up being exactly identical to reflecting over the x-axis? Do either of the greens match any of the oranges in every single way? No, they don't. They're remarkably close though, right? But they don't match perfect in every single way. Neither one of these greens is the same as any of these three oranges, which means reflecting over the y was not the same as reflecting over the, reflecting over the x. That hole in the paper really messed me up. Therefore, this is also not odd. This did not make its way into the video that I recorded and uploaded yesterday for help on the extra credit sheet, the characteristics and properties of functions help. Even an odd symmetry didn't make its way on there, even though that's in the extra credit. So, there we go. So it's just a good little spiral overview for you. Tying the concepts together, transformations along with symmetries. We good? Okay. Question? All righty. The last transformational category that we're going to talk about is dilations. We've covered translations. We've now covered reflections. And lastly, dilations. Dilations, there's actually two kinds of dilations. There's stretching and there's shrinking. But they're both considered dilations. This means objects getting smaller or bigger. Okay? Like the pupil, you can say your pupil is dilated. That literally means it's changed size, either got bigger or got smaller. Okay. Alrighty. How do we recognize a translation? Adding or subtracting somewhere. How do we recognize a reflection? Multiplying by -1 somewhere. How do we recognize a dilation? Multiplying by any other non-negative number. If you have a non-negative multiplier. Well, Mr. M, what if I did have a negative multiplier? What if it said times -2? The negative symbol is its own transformation. The negative symbol is the reflection. So if you saw a times -2 somewhere, the negative was a reflection, and then the 2 was the dilation. the non-negative number is the dilation. That's why it says let C be any positive real number. If you have a positive multiplier somewhere, then these are how you get stretches and shrinks. And now I can go back to talking about inside opposite effect. But again, it is easier to talk about vertical transformations first. When you have to have a vertical stretch or shrink, vertical is your y values. Y changes happen outside, and that's why you see me put the times C here. This is a multiplier on the outside. And outside changes, y changes, vertical changes behave exactly the way we think they should. Let's talk about a y value that every one of you has, your height. Your height can be considered a y value. If I multiply your y value, your height, by 2, did you get stretched or shrank? Stretched. You see, multiplying by a number on the outside, multiplying a y value did exactly what you think it should do. Multiplying by 2, yeah, that stretches an object if it's the y values. If I multiply your height by 1/3, you're going to be really short. You got shrank. Which means multiplying the y values by a number has the exact effect that you think it would have. So what does this do? This literally multiplies your y values by C. If C is bigger than 1, remember C is positive, stretch. If C is smaller than 1, remember C is positive, shrink. If C is negative, remember the negative part is a reflection, the number part is the dilation. Cool? I've said it a few times now. Great. So what this does is it literally multiplies your y values by whatever C is. And then you would say you have a vertical stretch, factor whatever C was. Vertical shrink, factor whatever C was. Not if it's negative. The negative is its own job. You see a -2 on the front? That's a reflection over the x-axis and a vertical stretch, factor 2. You would have to say both. Well, the good news is all you would have to do to the y value is multiply all the y's by -2. So that job is easier, but the description requires 2 things. Oh man, those troublesome x's, right? Man, there's a reason why we dump them. There's a reason why there are x's. They just don't do what we want them to do. Well, multiplying by a number on the inside has the exact opposite effect that you would think it has. Multiplying by 2 on the inside, you're thinking, that's going to double those x? No, actually it doesn't. It cuts them in half. It has the exact opposite effect. But we don't want to say divide. We don't want to say divide by 2. Instead, we'd say multiply by 1/2. You see a 1/3 in front of your x's. You thinking that thing is getting skinny. Actually, it's getting wide. It's literally tripling your x values. So what do? Our multiplier is a reciprocal. That means flip the fraction over. Multiply x values by the reciprocal of C. That means flip the fraction over. So if you see a 3/4 in front of your x, you think to yourself, okay, that's actually multiplying by 4/3. That's bigger than 1. That's a horizontal stretch. If you see a 5/2 in front of your x's, what you're actually multiplying your x values by is 2/5. That number's smaller than 1, horizontal shrink. And as always, anytime something's going on right here, it is a substitution. In Algebra 1, your teachers probably taught you the word, or maybe even pre-algebra, I'm not sure, PEMDAS, right? Which, by the way, is not a word. It's an acronym where each of the letters stands for something. It's parentheses, exponents, multiplication, division, addition, subtraction, right? Each letter stands for something. You know other acronyms like NASA, National Aeronautical and Space Administration. You know other acronyms. You've used them. If you've taken geometry, you've heard of SOHCAHTOA probably. This is an acronym. It's not a real word. Well, I'm about to teach you a new acronym. HIOVAS. HIOVAS is your transformational buddy. It will just tell you how the transformations work. It stands for horizontal. Now, horizontal transformations happen where? On the inside. And what kind of effect do they have? Opposite of what we expected to happen. Go Gators, just wrote in blue, about to write in orange. So that's what HIO is, horizontal, inside, opposite. VAS, vertical. All vertical changes happen outside of our function notation, and they will have the same effect we expect them to have. HIO VAS. And there it is. You guys didn't have any questions about reflections, so let's go ahead and put some practice into dilations. Here we have f of x equals x to the third minus 16x. You don't know what that graph looks like, and you don't need to know what that graph looks like, because transformations affect all functions the exact same way, which is fantastic. Now, it is unfortunate, again, you kind of have to be here to get the full impact of the lesson, because on my screen that won't make it into the video, I actually have the image of that graph. So that's what it looks like. I just wanted you to see it. Cool? There it is. Okay, let's do some work with it. This first one says vertical stretch factor 3. And again, this is where second period kind of dropped the ball a little bit. They weren't answering questions in class. If it's a vertical change, is that going to be changing my x's or y's? Y's. Okay, I had less voices than normal. Is it because we struggle to remember which one is which? Maybe that's what it is. But remember, if you look out the window to see where the sky meets the ground, it's going to look like a horizontal line called the horizon. The word horizon comes from the word horizontal, okay? So vertical is up and down, which means it's your y changes. So this is a y change. Since it is a y change for my function notation, is it going to be on the inside or outside? Outside. Y changes will always happen on the outside of the function notation rule. And lastly, because it's a y change outside, vertical, will it have the same effect or opposite? Same. VOS, VOS, same effect. What that means is, because I saw the word stretch or shrink, I know I'm using a multiplier. And what I've written in blue tells me what I'm multiplying by and where I'm multiplying by it. I am multiplying by the same number, so I'm multiplying by 3. Where? Outside the function notation. So the rule for this is take your f of x and multiply the outside by 3. That is the rule for it. We can now use that rule to figure out our new equation that we will call g of x. Here's f of x. And here is me applying my rule. If I multiply the left by 3, I have to multiply the right by 3. Yes? And that is a wrong answer choice waiting for you on my test if this is my test question. It's worth half credit though, because the student understood they were multiplying the outside by 3, but they didn't do it right, because you have to multiply the entire side by 3. Please get in the habit of, when multiplying a side by a number, using parentheses. You have to distribute that 3 to get it 100% correct. This is g of x now. Distributing the 3 gets me a 3x to the third minus 48x. Earlier, someone asked me why I did not multiply to that exponent. Because only exponents can affect, actually, how do I want to say it? Okay, exponents of polynomials can never be affected by transformations. And try not to get too confusing about this. How about this? If I had multiplied this exponent by this 3, this would have been some kind of x to the 9th graph, which shape of the graph is drastically different. It introduces a lot more wiggles, and transformations can't do that. Transformations can take an image and move it around. Transformations can flip it upside down, or flip it left, right. It's kind of hard to see with pens. That didn't really make much sense. Oh, I could do this, And transformations can stretch them or shrink them. Transformations cannot turn this straight pin into a wiggle. And that's what would happen if you altered the exponents. Okay. Now, again, there is a reason to be in class because you get to see more stuff than what you can see in the video, because this is not recording my screen. It's recording what my camera sees. So I show you guys this image on Desmos, and it still sees the notes on my paper. So I'm waving at the video. Okay. Here is the equation that we just got. Now, you might be thinking to yourself, that graph looks skinnier than the red one, right? Does look skinnier, doesn't it? But I can prove to you that it is not skinnier. Again, this is the perk of being in class and seeing the lesson. I can prove to you it's not skinnier. So look at the red one. See where that x-intercept is and that x-intercept is. And hopefully you can see that from -4 to +4, those two x-intercepts are exactly 8 away from each other. Yes? Now, we turn the green one on. And I look at its x-intercepts and see that they are exactly 8 away from each other still. The width of this graph did not change. Only its height. And I can prove it's the height. This maximum y value is at 24.6. This maximum y value is at almost 74. So yes, the y's are what changed. But how would you know that it wasn't a shift? Because not every point with the same distance, the same direction. This red dot had to have gone up, while this red dot had to have gone down, guaranteeing for you that it's not a shift. Okay? Again, one of the perks of being in the lesson. But wait, that's stupid. Being in person for the lesson. There we go. Alrighty, let's do another one. Unless you have any questions for me about this that I have not explained already. Crickets. Okay. As long as you can promise there are no questions. Then we'll do this one here. Again, because I see the word, not horizontal, because I see the word stretch or shrink, I know I'm dealing with a multiplier somewhere. Inside or outside, I'm not sure if it's same or opposite effect multiplier, but the point is I know it's a multiplier. It says horizontal, like the horizon. So is that going to be an x change or a y change? X change. All right. So, let me use I guess I'll have to use purple. This is going to be an x change. If it's an x change, for my function notation, will I see the change on the inside or the outside? Inside. Okay, great. We'll see it on the inside. So we already know our multiplier is inside these parentheses. And since it's an x change, inside, horizontal, same or opposite effect? Opposite. Opposite effect. Now we have to be really careful here. It's not opposite multiplier, it's opposite effect. So what's the opposite effect of multiplying by 1/2?
2. 1.
Multiplying by 2/1. The reciprocal multiplier gives us the opposite effect. So we have a multiplier on the inside, but remember, everything on the inside is a replacement. So I'm not going to write the x black, I'm going to write the x red, because I'm going to replace all of my x's with a 2x. Reciprocal multiplier. That's what opposite effect means. All right, then I take my equation for f of x, and everywhere it had an x, I will open a set of parentheses because I am substituting. Plopping in a 2x. I accidentally put an x in my business. That was supposed to be a set of parentheses, so I could put a 2x in there. There we go. I'm going to show one more line of work before the answer. Because this is a multiplication, and only because it's a multiplication, and by the way, if it was a fraction in there, fractions are actually a kind of multiplication. But anyway, because it's a multiplication, and only because it's a multiplication, both of these objects will receive this exponent. It's not distribution, it's application. Both objects listen to that exponent. So it'll actually look like this. 2 to the third times x to the third. And then here, 16 times 2 is 32. So my new function, who we will call h because I've already used f and g, it's 2 to the third. Well, if you don't know 2 to the third, you could do 2 times 2. That's two numbers. So what's 2 times 2? 4 times 2, one more time. 8, there it is. Okay, so we get 8x to the third minus 32x. And that'll be the last example we do. Don't get packed up yet. Hold on. That'll be the last example we tackle today for the homework over the weekend. And it's a nice long weekend, so I'm going to suggest that maybe you do a little bit of it today. That way the knowledge is fresh, and that way you don't have to do anything on Monday. Whatever you want to do, it's just a suggestion. I suggest it to my son every week. He ignores the suggestion every week. But whatever you can do over this weekend, do. What can you do so far? Single transformational stuff. Now, I will stop the video there, but I'm going to show you guys Desmos. So that's it for us right now. Squeak a nerd sign on there because, it's a good thumbnail. And that's it for that.